All right. Hello, class. Mr. Pettibone here. Um, I I realize it's Memorial Day. Actually, I just realized that this morning after I had already planned my lesson. Um, so if you would prefer to watch this tomorrow, then you can watch it tomorrow. But I'm just going to do my lessons, and so yeah. Um, so James says 1 more week. What does that mean? 1 more week until uh, I think you seniors get too focused on how much time is left and just wanting it to be over with. You should enjoy every day of your life and not just be waiting for it to be over. Um, so a couple of items we're gonna have. So I'm probably not gonna do a lesson on Thursday. So it'll just be 3 lessons, and that just puts it at a nice stopping point. Um, and then some other stuff I wanted to talk about. I'm writing your last quiz, and it'll be finished this afternoon or this evening, and I will post that. It'll be due Friday. Um, and let's see. I can't remember if I said it already, but we're gonna also have a meme review on Friday. Okay, so that's where we're at. Um, so we're going to talk about 2 things today. It should be a fairly quick lesson. The first thing I wanted to talk about is is what is the meaning of Luigi asks, are we having a final? You're having one more quiz. That's it. And hello to everyone else watching. Fu, James, Rowan, Zach, and Alex. So what is the meaning of the space-time interval? Okay. Now remember the space-time interval. Gotta focus this a little bit. Focus, damn it. Come on. There we go. What is the meaning of the space-time interval? Okay, so what I want you to imagine. So remember, the space-time interval is denoted by ds squared, and it's equal to c squared times delta t squared minus delta x squared. Okay? And it's separating 2 events in space-time. So my question is, what if you were traveling at a constant velocity between the 2 events? Okay? So what if you were traveling at a constant velocity between the 2 events? So the first event happens where you are, and the second event happens where you are. Okay? Because you're traveling between the 2 events. So, basically when the first event happens, you start moving, and then when the second event happens, you're there when the second event happens. So you're there for both events. So because both events happen where you are, from your perspective, so from your perspective, delta x equals 0 because you traveled from the first event to the second event. So both events happened where you are. So I'm assuming that you're the origin of your own coordinate system, right? You're the center of your own universe. So, the first event happens at x equals 0 where you are. The second event happens at x equals 0 where you are. So if we calculated the space-time interval, you have ds squared equals c squared delta t squared minus 0. Okay? So we can see that that the time that elapses is 1 over c times the square root of ds squared. Okay? So basically what that means is that the space-time interval is related to the time that would elapse for you if you were traveling between the two events. Okay? Aisha, the grind does stop. Like I said, I'm not giving you a final, so I think that counts as not being that hardcore. So the space-time interval represents, or I'm going to say represents the time elapsed for a person traveling between the two events. Okay? So, and remember, everyone calculates the same space-time interval. So whenever you calculate the space-time interval between two events, that's telling you how much time would pass for someone who went between the two events. Okay? And you can see that the time elapsed involves the square root of the space-time interval. So that explains why if it's a space-time, or it's a space-like separation where the interval is negative, it's impossible because you would have an imaginary amount of time elapsed. Okay? So that's the first thing I wanted to talk about today, is what is the physical meaning of the space-time interval. Okay? The second thing I wanted to talk about is relativistic momentum. Okay? Now, when we're talking about things in relativity, I'm going to hold the shade here because this is not happy with the lighting. It's like not focusing very well. So when you have a vector in special relativity, the vector has a space component and a time component. Okay. So basically, vectors in special relativity have 4 components. They have an x, y, z, and a time component. Okay. So sometimes they're called 4 vectors. But because we're doing we're doing sort of like one-dimensional special relativity, see how we have time and space. We only have one spatial dimension. So our vectors in special relativity are going to have 2 components. Okay. So this is the momentum vector. a relativistic momentum. Okay, it is gamma mc gamma mv. So this is the time component. And this is the space component. Okay, and of course gamma is that 1 over square root of 1 minus v squared over c squared. Okay, so what you can see is that the formula for momentum is slightly different. Okay, it has this gamma out in front. Now, when you are going, when the velocity is much less than the speed of light, then gamma is approximately 1. Okay, so what you can see is that the formula for momentum is exactly the same as the one that we learned when something is going very slow compared to when something is going very slow compared to the speed of light, the formula for momentum is exactly the same. But if something is approaching the speed of light, then what happens is you start to have significant variations. Okay. Now, I want to look at the time component here. I could write the time component as mc squared, gamma mc squared over c. Okay. Now, you might have heard of the equation E equals mc squared. That's Einstein's famous equation. This equation is only true for an object at rest. Okay? If something is not at rest, then we modify the formula, and it actually turns out that it's E equals gamma mc squared. Okay? So what we can see is that the time component of the momentum is actually the energy divided by c. Okay? So another way of writing the space-time momentum is to write it as E over c is the time component, and the relativistic momentum is the space component, where when I say relativistic momentum, I mean gamma mv, not regular mv. Okay? So these two expressions are equivalent. So it's kind of interesting because when you talk about relativity, energy and momentum unify, and it turns out that energy is just the time component of momentum. Okay? Another thing, if we do the time component squared, c squared times the time component squared minus the space component squared, this is a constant for all observers. Okay, so just like the space-time interval, if we do c squared times time squared minus space squared, we get something that is the same for everybody. Similarly, it's going to be a constant for all the momentum if we do time component of the momentum squared minus space component of the momentum squared. That's going to be a constant for everybody. So let's see what is time component squared minus space component squared for momentum. So I have c squared times the time component squared, which is gamma mc, that quantity squared, minus the space component squared, gamma mv quantity squared. Okay? So we're going to get c to the fourth gamma squared m squared, that's the first term, minus gamma squared m squared v squared. All right? So gamma is 1 over the square root of 1 minus v squared over c squared. So it's going to be, if we square gamma, it gets rid of the square root. Okay? So now what I want to do is I want to factor out the m squared. And I'm also going to factor out the c squared. And I get, what do I get? C squared minus v squared over c squared. I feel like I'm making a boo-boo here. Oh, you know what? This c squared isn't going to be there. That's why. So this should be c squared, that should be c squared, and this would be 1. Okay. So you can see that these two factors cancel out, and I get m squared, c squared. Okay? So that is time component squared minus space component squared. And that's going to be the same for all observers. Okay? So basically, when you calculate this for the momentum, it tells you the mass of the particle. Okay? Now, what happens if we do time component squared minus space component squared, but we do it with this formula? So I did time component squared minus space squared with this formula, but what if I do it with this formula? I would get E squared over C squared minus relativistic momentum squared equals M squared C squared. Okay? And this can be written as E squared equals P squared C squared plus M squared C to the fourth. So this is the generalization of E equals MC squared for particles that are moving. Okay? So this is a very famous formula. This is the actual E equals MC squared formula. Okay? So I just thought I would show that to you. The other thing I wanted to talk about is this is the formula for momentum if you have a massive particle. But what if you have something like a photon? Okay? If you have something like a photon, you have, so the momentum of a photon, which is a particle of light, is going to be the energy of the photon divided by c is going to be the time component, and the momentum of the photon is going to be the space component. So it ends up that is hf over c, hf over c. and this is a plus or minus, because this depends if the photon is moving to the right or to the left. So F is the frequency of the photon, C is the speed of light, and H is called Planck's constant. And its value is 6.6 times 10 to the minus 34 joule seconds. Okay? So what are our key formulas for today? It's this one, this one, this one, and this one. Okay? So, 4 big formulas for today. So what we're going to do tomorrow is we are going to use the momentum of a photon to calculate the Doppler effect. And then on Wednesday, we're going to talk about the conservation of momentum and how that pertains to special relativity. And those will be our last 2 lessons. Remember, Friday's a meme review. We'll have no class Thursday. You're going to have a quiz that'll be up by the end of the day today, due Friday. All right? So have a great Memorial Day, and